And we will start with Rita's paper, and I think we've actually. Oh, here she is. Here, huh? Hang on, we'll get you to unmute yourself there if I can't unmute you. There you go. Hi, Rita.
Hi.
How are
Hi.
you?
Good. You?
Good. Thank you for joining us. Nice to see you.
Okay. It's a pleasure.
Hey, V, let's take off with that first paper, and then see how we do.
Okay, let's do it. Okay, so the paper is called Oceans of Stimuli, an individual-based model to assess the role of olfactory cues and local enhancement in seabirds foraging behavior. And basically, it's a paper that aims to understand different sensory and behavioral drivers of core shearwaters movements. So because resources in the ocean are patchily distributed, prey search capabilities are essential for seabirds, especially when they're breeding, and because they are central place foragers, they have spatio-temporal constraints on their movement. And so it is widely studied that procellariform species like shearwaters use olfactory cues to navigate and also to find food. And it's also been studied how other species of seabirds use transfer of information either at the colonies or on rafts, and also at sea to gather more information about where the food is. And so this has not been discussed in core shearwaters yet, which is why this paper is so cool. So what the authors did was they developed an individual-based model to understand how these individual mechanisms drive movement of shearwaters, and then they used real GPS data from core shearwaters of an island in Azores, in Corfu, to validate these models. So the aims were mainly to understand how well olfactory cues and local enhancement reproduce the movement of real core shearwaters, to set different environmental scenarios like poor productivity or baseline productivity and high productivity, and also to understand how different densities of birds would affect the efficiency of foraging birds, and see how the two olfactory cues and local enhancement, which is birds gathering information from neighbors at sea, affect the foraging efficiency or the energy gain of birds. Okay, methods are quite complicated, and because we don't want to extend or go to something too specific and too methodological, I will just gloss over them, honestly, because I don't quite understand them either. So there's two scenarios, like an individual-based model. Basically what it does is simulates virtual birds in virtual environments and give the model a couple of parameters of how birds move and reproduce movement of birds for several number of days and understand the energy gain with this foraging. And so there were 4 strategies that were tested. Uninformed search, so virtual birds can't smell and can't gather information from conspecifics. Only olfactory search, the only thing birds can do is smell the productivity patches. Local enhancement, so the only thing that birds can do is gather information from neighbors, and then both combined, olfactory and local enhancement search. And then the scenarios were based on the real scenario environmental characteristics of the real GPS data, which is baseline, then poorer productivity scenario and a higher productivity scenario, and then 4 different levels of seabird. And to simulate the tracks, they use the characteristics of real life data to simulate area restricted search and commuting. And then compare the tracks produced to the real data to see how well these are reproduced under 4 scenarios, or 4 scenarios and 3 environmental conditions. So basically, the reported results of this paper are in figure 5, which is the one with the lines of the different energy gains. Basically, the strategy that best reflects the reality, the real tracks, is the one that combines olfactory cues and local enhancement. And the thing that's really cool is that it reproduces the spatial segregation between 2 subcolonies that are sampled. So birds are from one sort of colony divided in 2 subcolonies, and the birds, real birds from these 2 segregate in space, and the virtual birds, when they use both a local enhancement and olfactory cues, do too. Another thing that was interesting was that none of the virtual birds under any of the circumstances gained any energy in the poor environmental characteristic scenario. And then under good foraging conditions, the combination of olfactory and local enhancement and just the olfactory search strategy were consistently better than the other two. But local enhancement needs high seabird densities to do well. Local enhancement with low seabird densities doesn't do as well as the other, which makes sort of sense. And especially under normal environmental conditions, local enhancement is needed. So gathering information from other individuals is needed to obtain the same energy gain as when environmental conditions are especially good. So it sort of compensates for not so good environmental conditions. And I think, as I said, the important, or at least the more curious thing to me was that with olfactory cues, the virtual birds reproduce the segregation between colonies, which is really cool. Because segregation between colonies is a thing that has been discussed a bit in other species, but we don't really know where it comes from or what drives it. Also, I think the fact that in very poor conditions, none of the virtual birds gained any energy means that birds must have another strategy to increase their efficiency that has not been introduced in the model, which is also cool because what is it and how can we know what it is? And then also that local enhancement is not really sort of necessary if environmental conditions are really, really good, which to me says that local enhancement evolved in order to improve foraging efficiency of birds, because they actually did need it. And then another cool thing is that there's sort of a synergy between both olfactory search and local enhancement, because the two combined produce a higher energy gain than the sum of the two alone, which means that they not only add up to each other, but they sort of complement each other really, really well. And there's a lot of stuff in this paper, but I think, well, at least to me, maybe this is biased, but this is the most important, interesting things of this paper. And just to start the discussion off, and then people can add on with their questions, I have two sort of general questions. The first one for me, Rita, is exactly about the spatial segregation between the two colonies, because it does seem to reproduce what the real data do. But I wonder if you do think there's something else apart from smell, like maybe orientation of the subcolonies, if the birds only can go in one direction because there's cliffs either side or something. Is there something else apart from that that you think can be driving that? And then also because you used only one day trips, because obviously there's only so much you can add to a virtual bird. If you could have the individual based model of your dreams, what would there need to be in there so you could actually reproduce complex foraging patterns like dual foraging strategy, self-provisioning, chick provisioning, all that kind of stuff that makes seabird foraging so complicated. And
Hi, Virginia. Thanks a lot for your comments on my paper. Yes, I think you touch really important points. And this spatial segregation is, well, quite interesting and I would say tricky at the same time, because, well, in fact, it was the olfactory guidance that birds had at the colony departure that trigger these bias in the direction of birds in a perpendicular direction to the coastline. Mm-hmm. Well, it actually when I was doing the review of the paper, the reviewer, he asked me the same. Don't you think there's another mechanisms underlying this pattern? Well, yes, I think so. That's why I discussed that, and because one of the things I guess have a major rule in this pattern. It must to well, it has to do with the short-term memory, and also some kind of colony information transfer that combined with local enhancement might trigger these or might underline this mechanism. In our, well, we don't have memory, neither short-term information in our model, so the model is not ideal, and a model is never a finished product, right? So that's something else I add in the final remarks, that it would be really interesting to include such kind of mechanisms in order to accurate these predictions and the real explanations for the mechanisms behind. What else? This is concerning spatial segregation. And
yeah, the other question was, what do you think the model needs to include as well? Even if it's not possible technically right now, just to reproduce the complexity of core issue waters.
No, it doesn't. I
It's
need
impossible,
to add. It's impossible. Yeah, that. Well, we can add new things and new mechanisms to the model, and the model can become really much more accurate, but also complex, right? In models, we want to recreate the reality in simple terms, or as simple as we can. So yes, we could add, for instance, I think energy budgets and, for instance, allocation decisions would be needed in order to as you said, to for instance, to recreate the dual foraging strategy. And in this case, it would be necessary to include not only short-term memory, but also long-term memory that they use during long trips. So, but this is quite complex to, I think, are you listening to me? Yes.
Fine. Yeah.
Oh, I lost Virginia.
Oh.
Okay. These well, so there's some combination of mechanisms that would need to be included in the model. So we could reproduce or extend the model to the entire breeding season, because this is one day local foraging trips around the colony. So and we don't even take into account environmental stochasticity, which is something also important to taking into account to understand, for instance, the role of short-term memory in their behavior and in their decisions, foraging decisions. I don't know where's Virginia is.
I think we think we've lost her. She was telling me earlier that she was having some issues. They were having some storms there as well, and I think they were having some issues with their internet. I know here in Scotland we've been hammered as I had some internet issues earlier, so I reckon that's what she's coming across at the moment. Presumably she'll try to join back in when she gets a chance. In the meantime, anyways, I wanted to say that, like, I was really quite impressed with the complexity in this paper. You've obviously put a lot of work into these models. What I really quite like about this sort of approach is it's the way you sort of test these hypotheses, where you're generating virtual birds and then testing whether or not they match reality. And I think that's quite a cool way forward when we're looking at these sorts of questions. I had kind of a question that was more about sort of like the chemical sensitivity of these birds. So this is kind of falling a little bit out of the modeling aspect here, but what I'm curious about is if you think there's the possibility that these birds may be reacting to different different types of chemical cues. I mean, you're probably familiar with the work that Gabby Nevin has done on dimethyl sulfide and such. And obviously, in this paper here, it looks like you're using chlorophyll A and sea surface temperature as sort of proxies for productivity. And do you think that there's any potential mechanisms here associated with differing chemical sensitivities? So, are they focusing? Is it DMS that you think is the mechanism here, or is there another chemical cue that may be playing a role?
Well, that's perhaps there is another chemical sensitivity, but I don't know. What do you think about that?
Well, I'm just wondering if do you know of any like experimental work that's been done on Corey Shearwater's, looking at what that mechanism is or what the particular chemical is. Because if you look at a lot of the work on procelariforms, obviously has been done on DMS, but there's been evidence as well that they're attracted to other forms of oil. Or is it maybe just a generic?
Yeah, in my model, you mean in terms of modeling?
Yeah.
Oh yes, in terms of modeling, is just a generic. There's no specificity about if it is DMS or something else. Actually, my birds, they have olfactory acuity of 20 kilometers ahead, and in a radius of perception of 180 degrees. And that's all, it's really generic.
Yeah,
it's really generic. So it can be for DMS or and these are the kind of things that the model can be more accurate if we can include real parameters, for instance, to DMS or to another one which olfactory acuity may change. I don't know.
Yeah.
And that can be included in the model, but at this level, at this stage, I just include, more general.
So that sort of leads into the question of whether or not you could use like an isoscape. So I guess it wouldn't be an isoscape, but an odorscape. Do you think that the inclusion of an odorscape into your models would improve the output?
Yes, for sure, definitely. Yes, it would be really nice, really, really nice. Because then, instead of these like generic rule, okay, you can smell in 20 kilometers ahead, and we could model and maybe also with wind fields, and there's a lot of things that we can improve in our model, and another landscape would be really nice.
Yeah.
Really nice, yes.
Hey, Virginia, you're back.
I'm back. Sorry for that.
I sort of thought that your building was hit by lightning or something.
No, but somewhere some phone signal tower was, but I'm back, apparently.
So she did finish answering your last question there. So do you have any other questions for Rita while we're at it?
I mean, I could be asking all afternoon, but if someone else has a question, I can wait.
I haven't seen any hands, but if anyone has a question, please raise your hand or wave your hands frantically at your camera if you can. I think there's only a couple of us who have cameras on today, so. But nobody's raising their hands, Virginia. So I think you're clear to ask your next question.
Okay, so I think this is sort of what you were talking about. Like at some point in the paper, you discuss how the orientation of where olfactory and visual stimuli come from is what can have, like in the sensitivity test, like can have more effect on the longitudinal segregation, sort of, if I like. At some point, you discuss how olfactory and visual stimuli, and not the stimuli, but the direction they get them from, like the angle, is what changes the output of the model a lot. Like in the sensitivity, these are variables that come a lot.
Yes. Uh-huh.
I-
So,
yeah,
uh-huh. Yeah. The sensitivity analysis is
yeah, that-
a test we do with models in order
Mhm.
to understand which are the parameters that when they change, they produce major changes in the outcomes of the models. Okay.
Mhm.
So it's like the model sensitivity to the parameters used to parameterize the model. And in this work, the parameters, where are they? Yeah. So according to my results, the perception, the speed of area restricted search
Mhm.
and of traveling or commuting,
Mhm.
visual acuity, and the perception angles of olfactory and visual stimuli were the key parameters in the model outcomes. So this means that the model, those are the parameters that we should have more. We should be certain that they are
Mhm.
the accurate as possible. So the model don't give results that are with a very high bias, I would say. And yes,
Yeah.
those were the more sensitive parameters. Since I have the speed of ARS and
Mhm.
traveling is based on real data, I'm not really preoccupied with this, right?
Yes.
Then I have visual acuity and perception angles of olfactory and visual stimuli. And I was talking with Grant before when you just
Yeah, I suspected that this is a question that you have sort of answered, but
yeah, that the model has really generic rules regarding these kind of parameters. So it would be really nice to have much more accurate values regarding these parameters to improve our confidence in model predictions.
this is the same parameters for both subcolonies, right? That you input the model.
The very
So
same.
I guess the difference, like what gets me is that it's olfactory cues that are the ones that are helping the model reproduce the segregation more. And I imagine if the angles of where the birds receive the smells, like the olfactory angle is the same in both subcolonies, that must need to do with the angle they are leaving the colony.
Yeah, it has to do with the angle that they are leaving the colony, plus the fact that they can start smelling some or tracking some olfactory cues just from the beginning of the trip. So they are
Okay,
like
they can
pushed.
smell things from farther away that they can see.
So they are like pushed in front.
Okay, I see.
That's why I think the model is giving this clue that
Nice.
well, we need to try to understand in base of field work and something, and might, well, as I said, it's not easy to understand just from the point of view of olfaction.
I guess those results could be confused with what would happen if they transfer information at the colony. So if birds know where to go because some other bird has told them in some way, the effect would be the same as this if they are
Exactly.
smelling things far away.
Exactly. Yeah, yes, yeah, that's it. That's something, that's an hypothesis that I rise in this when I was discussing these, that the rafts, for instance, in the morning when they do rafts before leaving the colony, they might gather some clues from other birds that just fly away and don't stop in the rafts or in the rafts, and they just following those birds in specific directions, and
Yeah,
you can understand.
Yeah. I was wondering if there's a way you can add that to a model as
Yes,
a
totally.
parameter. That would be so cool to check.
Not
See if the
not
model
just,
can differentiate between olfactory cues and
yeah. Yeah. Well, like a mechanism, I could test that mechanism in the model. Yeah, but in that case, I would need to include short-term memory, or
I see. Okay.
otherwise, or yes, I could just test with a parameter saying, let's say, okay, this percentage of the individuals have information towards
A productive
a
factor,
given
so.
place, and let's see what happened.
Okay, this is so interesting. I could be nerding about this for all afternoon, but I don't know if how fast. Maybe it's time to.
But we've got a quick question we got a question here from Lucas. So I'll get Lucas to say, I'll lower your hand here, Lucas. Hey, how you doing?
Okay. Hello, Rita. Hello, everyone.
Hello.
Nice to see you.
I have actually, I'd like to throw in an hypothesis and see if it makes sense at all. Is it possible that a bird leaving the colony could be following like the other trail that a previous bird did? Let's say, I don't know if it's possible that a bird would lead like an other trail,
Yeah.
and the other bird would follow in this trail. Is it possible to incorporate things like that on a model?
Totally, but you mean because in the case of shearwaters, they leave the colony in the morning and they just come back in the night, as you know. So you mean because there's another species that they return to the colony a lot of times during the day, and the rafts are one of the hypotheses is that the rafts are used so birds in the rafts can track the returning trajectory of the birds. So in that case, they know that if the birds are coming from that way, that's the way I want to track, because there's food. But in the case of the shearwaters, that doesn't happen during the day. So that's why I wonder if the rafts in the morning might be used to track successful birds from the previous day, for instance, because if a bird, he was successful in a given area today, tomorrow, he will try to go there in the first place. So that could be a possible way of information transfer at the rafts in the specific case of Chorus shearwaters. I don't know, it's my idea.
Well,
I mean,
actually, I asked that.
Shearwaters do smell a lot, and they seem to actually recognize, or maybe they recognize individuals by their smell. So maybe they could. Is it true that there's such a long time between the time they leave and the time they come back that maybe the leaving out trail is gone? But in any case, the patch they're interested more is the last one, because the one that's most likely to be there still when the birds go back to the colony. So if other birds at the colony were able to follow the smell of the returning bird sort of reverse,
okay,
from the most smelly to the least smelly until they find the food. I think that was what Lucas.
But they yes, Lucas.
Okay. That's exactly what I was trying to say. Actually, I was going to give an example that happened to me with a species I'm working with. We have 3 neighboring nests, 3 females. They left and they did almost the same tracking, but the first one left, come back. The second one left and did practically the same route of the previous one, and then a third one follow in. So it was like the second one was going after a trail of the first one. So I'm not sure if this kind of stuff happens, but
that's really interesting. But
Yeah, it's
How do you model that?
hypothetical. Yeah, it's hypothetical, and
Yeah.
I have no way of explaining that with the data I have.
But
So
don't you think that your birds, they all knew about that patch before, and they were not just...
yeah, that's possible too. Yeah, definitely, that's possible too.
Yeah. Cool.
Well, I don't know. Yeah.
No, that's great. That's great discussion, guys. I think we should probably move on to the next paper though before we keep getting keep going down this rabbit hole. It's as it typically is when you get into good discussion. Hey, thanks for that question, Lucas. Rita, thanks for joining us. Thanks for that really cool paper.
Thank you.
Again,
Thank you, Virginia.
Thank you.
Thanks for doing that, V. And I think we'll move on to the next paper. We've got Ellie Bowler with us. So where are you? There you are. Hello, Ellie. Let's see.
Hi, how's it going?
Good. Nice to see you again. How have you been?
Yeah, you too. Yeah, pretty good. Not too bad.
Yeah, good. Sorry, I just realized I've got the mountain rescue helicopter is literally just about to fly over my house, so it might get loud for a second. This is the problem with living up in the Great Glen, and we have Lossiemouth uses the Loch Ness and Loch Oik as a training ground, so we'll get fighter jets coming down like 100 feet over the house most of the time. Typically, it's quite disruptive on Zoom calls. But anywho, this is quite a cool paper, and Ellie, since we first met a few years ago, I've been quite looking forward to this paper coming out. So I was excited to see it. So let's get into it. So we all know monitoring populations of seabirds is a really vitally important task, and has wide-ranging implications on sort of how we approach management, and as well as how we keep track of ocean health. And this is typically done via manual ground counts, or more so nowadays using drones and things like that. But for those of us who have really done any census work with seabirds or spent time in the colonies, you'll know that in some cases it can really be quite disruptive to breeding efforts. Now that's assuming that you can actually get to those colonies in the first place. And you know, seabirds breed in the most insanely remote regions of the world. So the question is, how do we begin to go about monitoring populations of birds that require expensive and potentially dangerous field expeditions, especially during a time when funding may be scarce due to economics, the economic situation. And certainly that's going to be highlighted in the next year or two as we get through this recession, or due to the impending climate impact of researchers traveling long distances for data collection. And of course, one way to go about that is through the application of remote sensing technologies. Space assets are increasing in availability rapidly due to the larger number of satellites that are in orbit. For imagery, for example, one of the most high-resolution satellites available is WorldView 3, which is operated by Maxar, which used to be Digital Globe, and they've sort of rebranded. So this satellite can capture 31 centimeter resolution images from low Earth orbit. And in the past, it's been successfully applied to find whales. Now, this particular study, which is led by Ellie at the University of East Anglia, focuses on a colossal, conspicuous, and charismatic seabird, the wandering albatross. Wandering albatross breed in the Southern Ocean in places like South Georgia, the Kerguelen Plateau, and colonies can really only be accessed after long, expensive journeys on ships. Now, aside from penguins, penguin colonies on the ice, these big guano patches, wandering albatross are really a nice candidate for the application of satellite imagery for a few reasons. One of those being the size of the birds. So these birds are huge, 3-meter wingspans on the ground. They can be up to just over a meter and a half long. So that means you can see them in 31 centimeter resolution imagery. Albeit now these are just a couple of pixels on a screen, and I'll share my screen to show one of the figures from Ellie's paper to show what these dots look like, but it's quite fascinating. The other really cool thing about this is that wandering albatross and their breeding colonies are contrast relatively well from the background. That's because the islands they breed on, certainly at particular times of the year, tend to be quite green, and the nests are separated enough that you can see individual nests. And that's unlike a lot of other seabirds. They're very colonial, and where it's difficult to count individual birds. Now you can imagine that the manual effort of going through a satellite image is substantial, especially when looking for little white dots on a screen. So to overcome this, the authors of this paper employed a deep learning technique called convolutional neural nets. It's commonly used for object detection problems in imagery. And so just for reference for those people who don't know, deep learning is actually a subset of machine learning, where the learning, which is being done by the machine, is done over many, many layers. So hence the term kind of deep learning. These convolutional neural nets are commonly applied across a number of different areas of image recognition. You see them often in like automated cars and facial recognition and things like that. But they've never been used to detect individual birds from satellite images until this study. Now, this paper aimed to do a couple of things. There's been some previous work that's shown that you can count birds from satellite imagery, and this sort of follows up on that. And so the goals of this paper tend to be more around the methodology and the more technical aspects. But two of the main goals were basically to identify issues with observer bias. So if you have a bunch of people looking at these images, how much they agree with each other. That helps to identify what's called the Bayes error, or in other words, sort of like the best possible performance you might expect a machine to have using humans as sort of the gold standard, with the idea that humans are able to identify things in a picture much better than computers can. The authors also wanted to look at how choices in the ground truthing labels impacted metrics of model performance. So if you trained your model, if you taught your model with a certain subset and then tested that model with a different subset, how would that separate subset and that selection impact your model performance? So the authors used imagery from the WorldView 3 satellite, so 31 centimeter resolution, and for 4 colonies, 2 on South Georgia, or around South Georgia, and 2 from the Crozet Islands. Imagery was collected under a variety of different atmospheric conditions. So there was some cloud and clear skies, and the images were taken at different times throughout the breeding season. The imagery was also assessed by one experienced observer who was used sort of as the reference, and this is someone who's had a lot of experience looking through satellite images, and then 5 novice volunteers, so people who are basically coming into it new. Now, I won't dive too much into the technical details of the convolutional neural network, but if you get a chance, I would highly recommend reading the section on the paper if you have the time, because it's one of the best descriptions of convolutional neural nets that I've read certainly in a wildlife context. So if you go through it, Ellie and the other authors do a really good job of describing what the convolutional neural network does, which is often a bit black boxy to most people. So I highly recommend going through that. In short, sort of the authors use a technique called transfer learning, where you take a pre-built convolutional neural network that has a structure to it, and then you feed it information. And this is particularly helpful when you've got a very small data set to work with, which is what the authors had here. Now, to test the impact of the selection of ground truthing labels, the authors used different combinations of labels as identified by the experienced and novice observers. So, for example, in one case, only points annotated by at least 3 observers that were all identified as an albatross were used for ground truthing. Or in another case, there was random shuffling of observer labels. The total count, so it was quite interesting looking at the outputs of this, and almost not surprisingly, was that there was a lot of difference between observers, particularly in the larger colonies, where counts in one case ranged from 612 to 994 birds. So there's quite a lot of variation. The other really interesting thing was that there seemed to be a really strong relationship between island and agreement between observers. So one of the islands Apotra's Island. Apotra's Island. I'm probably
I'm not sure.
yeah, I'm probably destroying the pronunciation of that, but that had tended to have much more agreement between observers than any of the other islands. With Aninkov, now Aninkov Island is in South Georgia, off South Georgia. That one had by far the lowest amount of agreement, and it was consistent across all observers, all simulations in the study here. So that was quite interesting. When you looked at how observers scored with regards to accuracy against each other, in all 4 islands, the best mean accuracy was achieved when at least 3 observers agreed on if the target was an albatross. So if you had 3 observers agree that that was an albatross, that particular set of data typically had the best overall accuracy when you compared it to the other observers. So finally, the authors assessed different subsets of those ground truthing data and found that with the exception of 1 island, the model was robust with regards to overall accuracy, which means that it didn't really matter what kind of subsets of the ground truth you used for ground truthing. The model still produced relatively accurate or at least consistent results. So that was quite cool. And again, like, this is such a cool paper, and I want to congratulate you on the complexity and the technicality you put into the description. It's a very, very good read. So what I want to do really briefly is I just want to bring up a figure from your paper, which I know I had here on one of my things, or I had here. Oh, here we go. The reason why I don't have it up is because I didn't click open. All right, I'm going to share my screen with the folks here. For those of you who are able to follow the screen, hang on there. Where are we going? Basic. Screen 1, that's the one I want to share. Okay, so hopefully you guys will be able to see this. Just let me know. You see it all right? Okay. I want to go down and I want to show you this figure because this gives an idea of what Ellie was looking at here. So here we go. These are images from various islands. So BI is Bird Island, Aninkov, Apotras, and the name of this island I've completed, Grand Kutra, I think, or something like that.
Yeah, Grand Kui or.
Yeah. But if you can see, like, these are albatross here sitting on nests, and they are literally just a few pixels wide, just little white dots. But as I had mentioned, you can see how the background is quite green and contrasts quite well. So that's really quite cool. Now, so my first kind of question is. And looking at this image here, you mentioned in your discussion that image augmentation techniques could potentially eliminate some issues with the manual counts and helping observers locate particular birds. Do you think that the same augmentation techniques would also improve the estimates from the convolutional neural network? And if so, do you have any ideas on which specific augmentations would help?
Yeah, that's a really good question. And it's really nice hearing someone else summarize the paper. It was much better than I would have done it. Yeah, for augmentation, one of the main ones we talked about was the cloud cover, because that was only present in 1 of the 4 images. And so when we tested it on that image, it generally failed at picking up albatrosses under the cloud because the network hasn't seen any examples like that. Would be sort of 2 options for augmentation. Is either we could try remove the cloud, or we could try add cloud in to the training patches and see if that could help us out with the cloud cover problem. Other augmentation that we could look at is we didn't do very much in terms of varying the lighting conditions or the atmospheric conditions, which could be something that would be interesting to look at if we had more images. We could perhaps get an idea of if there's a certain set of atmospheric conditions that make it easier to see the albatrosses. Perhaps we could like enhance the images in that way to make it a bit easier to detect. I would say generally, obviously, because the network's trained using people's annotations, so if we can get people's annotations more standardized and kind of improved, then it should feed back into the network's performance as well, which is definitely something that we'd like to try.
Yeah, it's quite an interesting thing with these sorts of exercises, especially when you're starting from scratch. Like you're having to train the trainers before you can train the machine to train the
Yeah,
trainers.
it's a weird thing.
Yeah, so it's quite fascinating stuff. What kind of did you try any image augmentation techniques on your training data set? So did you try, say, simulating new data or augmenting your training data set in any other way?
We kept it quite basic. We did sort of randomly shift patches around a little bit, so the network didn't learn sort of, I don't know, specific location of albatrosses, so they were shuffled around, sort of shifted slightly, so they didn't appear in the same spot every time. And we also did kind of flip the imagery and reflect it in all the different axes, because it's aerial imagery, so there's no sense in, it can be any orientation, obviously, from the air. So we did those. Yeah, and then there's other ones definitely that we could try, but that's what we did in this sort of version.
Yeah. Are you guys going to be following this stuff up with some other colonies, or is this sort of it for now until the next project round?
It's we kind of currently trying to put together an application, so it's like very tentative, but we'd really like to, with the wandering albatrosses, it's quite good because they nest in like quite remote, spread out locations, but in terms of area, the colonies don't cover that much ground, not like with the whales where they can be anywhere in the huge amounts of imagery. So it would be kind of feasible in terms of collecting the imagery and purchasing the imagery to do like a global survey of every colony, which would be very nice. We'll see if that works out, but yeah.
Have you I know it's kind of convenient that these, where these birds kind of nest, where the colonies are, so you're not necessarily on a hunt for a needle in a haystack, which is quite convenient. I did notice that your images in the paper, you target a large area that sort of includes water as well. Were you able to spot albatross like flying over the water at all, or was it impossible to confirm that because of wave action and the like?
Yeah, it's interesting because there's sort of not enough information to go on to say if it's definitely an albatross flying over the water. I swear on one of the images you can see one like taking off the cliff. It looks like slightly different shape, but yeah, over the water, no. And I think we did this in quite a sort of, in theory, I think we could just remove the ocean completely. But for this one, we decided to train and see if it could learn that there weren't albatrosses in the ocean as well. So quite a pure approach and not remove any ocean and stuff like that. But I think in the future we could sort of remove the ocean because we're not interested, and also possibly build in a kind of aspect of like habitat analysis and see if we could just exclude regions which maybe are too steep to have any albatrosses in, or the habitat's not right, because that might sort of help us with the annotation as well. If people pick up white dots but they're not really in a place where albatrosses are likely to be, then maybe that can help with the confidence.
Yeah, that actually extends right into my next question, which was going to be, how 100% certain are you that what you're seeing is an albatross and not just a white rock?
It's really tricky. So the Peter Fretwell, who's my supervisor at FAST, did the original study which linked the sort of satellite image of Bird Island to the concurrent ground-based counts, because that's a really well studied area. And they found that the counts from the satellite image and the ground surveys were pretty much sort of within the sort of scope of what they should be, which was the way that it was validated. But I think confirming whether individual dots are definitely an albatross is really, really hard, because obviously you can't do ground-based surveys in all the locations. I think as a sort of core scale estimate, counting all the white dots, and then again probably adding in a sort of habitat analysis. And it would also be useful, I think, to give the images to the sort of expert observer we used, was a satellite expert, and has done a lot of this kind of analysis, but not specifically an albatross expert. And so maybe albatross experts would have a different view on where they're likely to be, and just an insight into different behaviors, like whether they nest near each other or the spacing of the nests even. There might be something interesting to look at in that respect.
Yeah, that's quite cool. So sort of, I guess, along that lines, but I mean, you've gone and you've applied a convolutional neural network here, and that's a relatively, no, it's gotten easier obviously, but it's certainly not it's certainly a bit of a daunting thing to get into, machine learning. But do you think that there's any merit in a more simplistic approach where you just say, you write a bit of code that just goes through pixel by pixel and looks for values that have an RGB value of 233, 233, 233 and higher, or something like that?
Yeah, I think that Peter tried an approach like that in his original paper, which wasn't published as part of the paper. I think he got a digital elevation model and thresholded on slope, and then did a habitat analysis and thresholded on NDVI, and then looked for white dots within a certain spectral threshold. So that's definitely approach you can use. I think one of the problems that comes up with those methods, commonly, they're now kind of called classical methods, but just not deep learning approaches, is that if you have images like we found with Apotres, where you have sort of unusual spectral distortion, or for example, if there's cloud, I think it gets difficult to kind of, sometimes it picks up stuff that maybe you weren't expecting in an image, and the deep learning approaches tend to be a bit more robust to those kind of unexpected signatures. But it's true, I think like maybe a combined approach where you do build in other factors it would definitely be interesting to look at, I think.
Mm-hmm. Yeah, just sort of something like that immediately, like image segmentation immediately springs to mind when you look at something like that. But
yeah.
Okay, I think I've asked a few questions here. I'm sure there might be someone with a question out there, maybe. I don't see any hands raised at the moment. I see there's a few. No, nobody. I thought I had a person waving at me then. But anyways, so and Virginia's gone, of course. I think we've lost her thanks to technology. So I will just continue on and ask a few more questions until somebody interrupts me. So the next question I have for you then is, how many times a year can you get images over specific colonies? And do you think that with the current the current number of available satellites and available imagery at the moment, is there a way that the method could be adapted to look at phenology?
Phenology.
Yeah. Yeah, is there a way you could look at how, whether or not you could look at the timing of when the birds arrive at the nest or depart?
Got you. Sorry, I'm a computer scientist.
That's all right. Sorry.
Sure, this yeah, so the satellite, they actually revisit almost daily the WorldView 3 satellite. So you can get very frequent images, which is another really good benefit, because usually you might go to an island and maybe do a survey over a week, but you can't repeat it. I think realistically, because of cloud cover and stuff like that, we'd be looking at, and in this proposal, we were saying we'd maybe get sort of several images over the nesting season, because that's quite long for wandering albatrosses. And not just from looking at the sort of timings and phenology and stuff like that, but also it might help us say, well, maybe there's a time of season where it's actually easier to see them. If like maybe the contrast between the grass is clearer or stuff like that. And also getting repeat images of the same island over the same season might let us see which actual specific dots maybe appear and disappear in certain locations, which would be very, very cool thing to look at. And definitely, yeah, it's definitely possible to get quite frequent images.
Yeah, certainly. I mean, I'm sure you're aware that Maxar is launching their Legion in 2021, so they'll be the frequency of satellite images is going to increase quite drastically in a few years. Virginia, you're back. I see. So, do you have any questions for Ellie?
I can't have a question because I missed half of the thing, so I'll just listen to everyone else's questions.
It's all right. I won't blame you for your failed technology.
I mean, I just came back and you straight on asked me if I have questions. How can I?
You should just be ready. Come on.
Nah.
Yeah, that's very cool. Now, the last question I had for you is probably more of a practical question, which is about the feasibility of this sort of continuing long term as a long-term monitoring method. Obviously, satellite imagery is very expensive, and so how would you foresee this becoming something that was cost effective enough to be able to be run by a program, for example? I know, for example, like BAS, because they're associated with Cambridge, can get satellite images under a foundational grant, but that typically isn't like it isn't necessarily near real time stuff, and there's still some issues associated with that. So do you have, in your work, have you come up with any thoughts on how it might be able to turn into a long-term monitoring program?
Yeah, I think so. The part of the reason for doing the automated analysis is to try reduce the cost in that stage of things, because at the moment it's very time consuming to analyze the imagery, and if we can automate that, then that would make it a lot more cost effective and you can put it through a program. In terms of purchasing the imagery, I think it is expensive, but then it depends compared to, say, in a lot of locations, compared to like going there on a boat or even flying a plane or whatever, it can be sort of roughly comparable or actually cheaper to get a satellite image of a location rather than going there. Obviously, it doesn't completely replace the need to go there because you can only get very coarse counts. But I think it's useful for monitoring. I think the Anenkov Island is particularly, I think they monitor that maybe every, it's in the scale of decades. So you have really big gaps in data. So I think supplementing areas where it's very important to get counts, it should be kind of feasible. I think it's realistic to get it sort of running at, as and when you need it, maybe.
Yeah, I think there'll be the need for people like BAS to invest in the program in the future to try and supplement any of the data that we can't collect because, for example, no one can go into the field this year.
Yes, yeah, particularly now.
Yeah, particularly now. It's just going to be heartbreaking for a lot of us Antarctic people who can't get down this year. So
yeah.
Anyways, I think that's all the questions I have for you. Is there anybody in the audience who has any questions for Ellie before we close up shop for the day? No hands raised, nobody throwing shoes at the cameras, so I think we're probably good. All right. Ellie, thank you very much. That was great to chat with you today. What a cool paper. Yeah, hopefully we'll see you again sometime soon. I'm sure we'll be in touch anyways over X, Y, and Z in the future.
Yeah, it's really nice to join.
And Virginia, of course, thank you very much for sitting in for David today and doing a fantastic job as usual, asking your questions.
Thank you.
And yeah, it was nice to see everyone. And I hope that you're all managing to stay safe and away from the madness of the world that is today. So thanks again. And next week we're back at 6:30 GMT. So an early morning one for the Australasian folks. So nice to see you all. Take care. Stay safe. And
bye.
Until next time.